Okay, so one thing that I want you to make sure you go over, this is from our lab. This is the Unit 2 technology overview. Make sure that you've got on your little formula sheet these things that's dealing with Excel as well. So for Unit 2, you really need to know how to do the binomial distribution. So you're always going to have to put that equal sign for it to let you know how to do these, that it wants you want Excel to do that function for you, calculations. And then the number of S is the number of successes, the trials, that's the number of trials, probability of success, and this cumulative value, right? So if you had some probability of success of 0.38, and you went out and grabbed, let's say 50 people, and then your counting variable is going to be from 0 to 50, the number of successes among this 50 people. Successive being a euphemism. This may be 30% carry a gene or a specific gene, and then if you went out and grabbed 50 people, what would be the probability of none all the way up to all of them? And this goes from 0, 1 through all the way, okay? And remember, this probability looked like n, choose x. Out of the 50, you would choose this many. And then you would have this probability of success to the x power, that's the success, and then 1 minus p n minus x. Okay. We don't do this by hand. We would do the binom.dist in a cell, and then we would go with the first thing is the number of successes. So if it's asking you for a specific number, you would put like 5. What's the probability of exactly 5? And then your number of trials would be 50. The probability of success, let me drag this over for us. Probability of success, that would be your 0.38. And then this is where the cumulative or not cumulative. Okay, if I wanted to add up, if I wanted to do, so this breaks out finally, okay? So if I'm asking for the probability of x less than or equal to 5, I would put this thing in here would be 1. If I'm asking the probability that x is exactly 5, then I would put that last number as 0. This sums up all the previous ones. Okay, so make sure you know how to use that. Okay, and write down your binom.dist. Make sure you can carry through with that. Okay. The next one you be careful, be careful. Where we at? Give me a second here. Let me reset. .56 is where I need to be. Let me hide this. And then you may also wish to use the binom dist range. I know I tend to this because I know how to use it, and I keep, and that's just normally the way the normal distribution works. Cumulative, it kind of reminds me everything goes. The binom.dist.range, you may prefer this one and use it for everything. Binom.dist.range. Some of my students use this for everything. And the idea is that you're going to do a little different here. So you're going to do the number of trials. We would have 50, the probability of success, like the 0.38, and then the range of numbers. So if you wanted exactly 5, you would need 5 comma 5. If you wanted between 0 and 5, say 5, 5, 5, this would be for the probability of x equal to 5. And then if you wanted the probability of x less than or equal to 5, you would need to do the 50.38, and then you would go from 0 to 5, binomial dist range. Okay. Let's erase this. Let's see what else we've got. Get it over here, bring this down. The normal distribution. The normal distribution you use, we've got a couple of situations here. Let me get back over. Once it goes too quick, it goes over to my other window. Okay. So the normal distribution, you've either got from a population, or you may draw a sample. Okay, you can have a sample over here. And then you can pull something, either an X or an X from this, but this is a particular individual. Either one works because I'm assuming that this is a simple random sample. Okay, so I've got a random version, it just happens to be into that sample, but it's going to be the same whether you were in the population. Okay, to use this, the way it is, this has to be a normal. It has to have somewhere in there that says the population is normal. Assume the population is normal. You do a random X, and sometimes they'll throw this in there. Okay, we took a sample from this, and what would be the probability? Either one is going to be the very same thing, that was less than some value n. Okay, in order for us to do a normal distribution problem, the norm.dist, to use this, it has to be a bell-shaped curve or normal distribution. It needs those two words. This is the better wording, but occasionally they'll say, okay, well, the population distribution follows a bell-shaped curve. The probability distribution follows a bell-shaped curve. Okay, and then once we do that, this is the fundamental. The probability that x is less than some number. You have to know what the mean is and the standard deviation from the population, and then you can come back and do the normal distribution. The x value that they're talking about is this number. So here would be whatever the big X is, okay? So the probability, let's put this in perspective. Maybe the mean was 220. The standard deviation was 20.5. And you wanted to know, well, if I picked out some random individual, what would be that measurement? What would be the probability that measurement is less than 200? Okay. What percentage of the population would have a measurement less than 200? The very same. Okay. So we would do this. The standard version is always to the left. So if this was 220, I kind of put this into perspective. Okay, so that's less than 220. That would be the probability there. Okay, so this thing would be 200. Left, less than, left. That's the standard that this is going to go by. Okay, so then you go over here. It says X, the mean, the standard deviation, and cumulative. So this, for our version, this is what you would put here, 200. The mean, the 220. Standard deviation, 20.5. Always, 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 for the norm.dist, this is equal to 1. okay? You always want the area. The only thing that 0 would give you is the height of this thing, and the height of a line is not an area. It is not the same thing as saying, well, I want x equal to exactly to 200. There's just an infinite number of numbers in here, right? Any two numbers, I can divide it and get another number in there, and I keep doing this thing. One little line, the probability of x being equal to 200 is just so close to 0, it's nothing, okay? So always put that as 1 to give you. If you're not, you're going to get it wrong, okay? It's not like the binomial where the values are either 1, 2, 3, 4, 5. There's a big difference between 5 and 4, and we know how to calculate those. So anytime that we're saying, what about if I wanted the number that's larger, what would be the probability? So here's my 200 again. If I wanted to know the probability that x was greater or greater than or equal to 200, this would be this area, okay? Norm.dis is only going to give you this. We know everything in the area is 1, and we just say, well, this area is 1 minus this stuff that we can do. Okay. So we'll do 1 minus the norm.dist, and it would be the very same, but it's 1 minus, okay? This thing right here is the very same as 1 minus the probability x less than 200. And this is what we just did. Okay. So here it gives you, there are 3 different scenarios that you're going to do. Here's the fundamental one, and it tells you this, the probability of x, the probability that the number less than some value, they just use a x1. That's that fundamental that I give to you. Okay, so that's this kind of situation. I got an x1. I want the probability to the left. Okay. For continuous random variables, not binomials, this is the very same thing as the probability x less than or equal to x1. There's no difference of adding that final line. Okay, there's not a big step in there like binomial. Okay, so this is what we would use. x1, the mean, sigma true. Okay, over here to the left. If I want the probability of x greater than x2, the problem could see probability of x greater than or equal to x2. Doesn't matter. This is going to be the very same 1 minus the norm dist. So let me kind of break this down. 1 minus the probability of x less than x2, okay, x2, and that's just the 1 minus norm.dist. That value, that x2 value, the mean, the standard deviation, and again, we're always using true. And then our final situation is when I want to know the range. So I've got some upper, the way they've used this is here's x3, keep all different numbers. I've got 2, it doesn't have to be symmetric. It could be over on one side, the other, open, it could be symmetric, but you're asking what is the probability that your random variable, if you picked out randomly a number, what would be the probability that it landed in this region? That's the probability of here, less than 6.4. And in terms of probability, this is always the biggest one minus that little probability in there. So this is the probability of x less than x4. This is everything to the left of x4 minus the probability of x being less than x3. and this is that area. So it takes the full area for the first one and then subtracts off that. And that's what this is equal to. That's how you do that. So for the norm.dist, we're going to do the norm.dist. X4, I got to pass it the mean, the standard deviation true, minus the probability, minus the norm.dist. And this is the X3. Mean, standard deviation, true. Just saves me some writing. But this needs, you've got to give it that to get any answers. Okay. So here's the full version of that. And it's the very same thing. This could be less than or equal to. That's what these pieces are saying. Less than or equal to. One-sided has that less than or equal to. One side can be closed, one side doesn't matter. You're going to use this very same thing. Unlike the binomial distribution, where you would take out, go and build your table. So you'd go 0, 1, 2, 3, 4. And if you had the probability at the most 3, this is x less than or equal to 3. This would include this, and this. So you want to add up those. If you had probability, so if it said, what's the probability that it would be less than 3? This you would only do 2, 1, 0. You would not do this one. You have to say this is the same thing as x less than or equal to 2, and then start adding up the probabilities. Okay. So the inverse function, is, we're going to use it a couple of different ways. As we go forward, we're going to find these things to find out critical values. Okay, but basically with the norm.inverse, we're going to say something like, what is that score that separates the lower, let's say 95% from the upper 5%? Okay, so the upper 5%, if I'm just given that, you'd say that's the upper. Here is the area that's in that tail. But when you come over and do, so this would be the norm dot inverse, it's asking you for the area or the probability, and it's to the left though. So even though you're given that point for the top 5%, you have got to do the 1 minus this. You would do 0.95. 1 minus, we're going to later call this area alpha. This top is alpha. So this would be the 0.95, and then you would pass it the mean and the standard deviation, and it would give you that x value that separates these two. Okay. Here it is, probability, the cumulative probability, or area to the left of the desired axis value. This is the area value, by the way. Okay. The mean, that's your standard deviation. So your x, not a z-score. If you did the norm, couple stars, if you did the norm dot s dot inverse, all you have to do is give it the area. But then it returns a z-score, right? Somewhere you expected negative 3.5 up to plus 3.5, usual negative 2 plus 2. That gives you a z-score. You would have to use this transformation. Let me go back. You would have to say, Well, you know your z-score is x minus the mean over the sigma, right? So if you were doing this to standardize z-scores, this is what you would do. If you go backwards from z-scores to your mean and your standard deviation, this is your distribution, multiply both sides by this, move this over here, your x value would be your mean plus z-score, the z-score that you would get, times your standard deviation. And that would give you this. That's if you use that norm.s. This is the standard. You don't need to give it the mean and standard deviation here because it knows that that's equal to 0 and your standard deviation is 1 for the standard. Okay. You could use this for the very same way, do mu1, standard deviation of 1, and this would be a z-score, not your x distribution. Okay. So it kind of gives you this little versions that you would be focused with. Just understand what it means, and then it's okay. Yeah, it's kind of a confidence builder. You go, this is what it means. Yes, but if you're just kind of struggling through these things, if you haven't practiced, all this stuff gets very cryptic within an hour. Okay. But here's the P. To the left, the probability has to be the left. So this is the probability that x is less than x1, but you're giving it now the probability, your mean, and your standard, and you're getting that x1 back. You pass at what probability do you want to the left? Okay. If you need it to the right, where your probability is to the right, then you got to do, and this is called the Q, right, with the area equal to Q, then they go 1 minus Q. So the top 10%, this would be 1 minus 0.10, that would be 0.9, okay? And if you've got some central area, and some of the problems they say, look, I want to know what the corresponding Z or X values are.
Mr. Webb.
Yeah, hold on just a second. Okay, so this is between the two. So it is saying if it wanted to know what these values are, and you wanted a middle percentage, right? So this is, let's say I want in here 85%, right? So this C, this thing is 0.85, okay? So that is their C, the confidence level in here that you wanted. This is later on. It's a confidence level. We're going to use this thing. And these Z scores, this is a plus Z and a minus Z. It's symmetric when I've got these two around. And it just says this is the easy way. Now you can go and say, well, the areas on the outside is 1 minus the 0.85, which is 0.15. And then half of it's here, and half of this area is over here. So this would be the 0.15 divided by 2. Okay, half of it, and this is called alpha over 2. Okay, so we'll kind of break there. Half of that, 0.075, and then 0.075. So instead of doing that, it just breaks this thing down for you over here. You would just say, okay, what are these? And you would say, well, either one of these, this one's going to be a negative and a positive. So it gives you, here's the negative version, here's the positive. Trust me, for this, for z-scores, it's going to be the same thing. But for your x values, it's not. Okay? So what they said, instead of going through and then going back and using that transformation, okay, you're going to just use, say, whatever, this is their x4, here is their x, this is your x3 in your distribution. You're just going to do x3, whatever this thing is, is 1 minus everything 1 minus the C, which gets you that, and then divided by 2, which is this one. Okay, norm dot inverse. It's exactly what you did, but you just typed that right in here. You can enter this as a formula as long as you got parentheses and do 2. So this would look like, for 0.85, you would do 0.85 parentheses. Let Excel know that it needs to do this first, then you do the /2. So it looks like this in Excel, /2. Okay. Lets it know that it needs to do this first, then divide by 2. That would be the probability. And then pass it your mean and standard deviation, and that would be your X. Okay, the next one looks pretty funny, but it works out. It works out to give you 1 minus this stuff over 2, and it turns out to be, so you would enter 1 plus 0.85 /2, and then give it your mean and standard deviation. And it'll do this for you. So let's say if we had this, let me go over this real quick. So if you had a mean of 220 and a standard deviation of 20.5, okay? So you had that, you wanted your X values, right? That for the middle 85%. Get my Excel opened up. Okay, so I would do, for the lower one, equals norm.inverse, right there. And see, it asks for the mean, the standard deviation. So you would enter, for that lower one, 1 minus 0.85 /2. That's getting Excel to do this for you, comma, and then you would do the mean, and then your standard deviation. And that would be the lower number, and the middle would be the 220. So 220, 190, and then if I do this as the upper, I would do the parentheses, the 1 plus 0.85, middle 85%, /2, that does the division, and then again the 220, and then the 20.5. And that would be above. So 220 is in between here, and then that would be symmetric about the 220. If I said equals 220 minus this number, the distance between the mean and that is 29, and then equal this, because that's a bigger minus the 220, it's going to be the very same. It's symmetric around the mean. Okay. So that's how you're going to use all of your norm and norm inverse. Okay. The norm.s, that's just, you've got to give it z-scores, okay? And this is, if you went to a z-score, you're going to use this. You could also do the norm.dis by saying the standard, the mean would be 0, the standard deviation is 1. And all of these are going to be the very same thing. This just, you don't ever have to give, when it's the s, so instead of norm.dis, norm.s, you're not going to give it your mean and your standard deviation, and it says, here's the z-score. It's going to use the mean as 0 and the standard deviation is 1, okay? The same thing as the inverse. You do not have to give it your mean and standard deviation because it's working with a mean of 0, standard deviation of 1. all it needs that probability or give me the probability and to the left, and it's going to give you corresponding z-scores. And it kind of looks like the very same set, the 1 minus c over 2 for the left side and then the positive side. These will be the very same numbers. Let me go back in if I get back here. So if I did this one, again, we said equals norm dot s dot inverse. So we had the probability to the left. If I did the 0.85, and if I'm doing, so I would do 1 minus 0.85 divided by 2, and it gives me that z-score. Now, if I do the positive version, norm.s.inverse, this looked like 1 plus 0.85 divided by 2. Really weird that it works out like this, that this gives you, but it does, and there's nothing else to give it. And this is going to be symmetric about the mean is equal to 0. Here the mean is equal to 1. I meant the mean is equal to 0. The standard deviation, the mu, is equal to 1. Okay? And it's symmetric about there. We're going to be using these later on. Next chapter, we're going to start using this. We're going to go through this kind of scenario, work backwards to get these. These are going to be called critical values. Okay, we're going to use these in calculations. Here we go. Start back up. I'm going to look at a few problems. Let's look at this thing. In 2014, Apple's market share of operating systems on smartphones in the U.S. was about 41.9%. You randomly select 11 smartphone owners in the U.S. Let X be the number of these people who have an Apple operating system. Okay, so this is the probability of success. We're going to do 11 trials, and then X be the number who have this thing. So the X would go from 0. None of them had an Apple operating system, all the way to all 11. Okay, so I just want to check the time real quick. So this, let me write down my pieces first. So your probability of success, that's 0.419. Okay, the number in your trials are 11. That's the sample size. You went out and grabbed 7 people. Okay, and then your X goes from 0 all the way to 11. 1, 2, dot, 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 10, comma, 11. Okay, 0 would be none out of the 11. Exactly 1, exactly 2. All of these are that very same. It's calculatable. This is the probability of a particular X. So this would be like X equal to 2. But the way we write this is the probability that we come up with 2. Okay, that shortens it down for binomials. Okay, so this would look like 11, choose 2. You remember n choose X, P to the X, 1 minus P. The non-successes, this and this add up to be n. Out of the n, X successes, the rest of them are not. So 11 choose 2, 0.419, that was our P, squared 1 minus the 0.419, and then this would be 11 minus 2, this power exponent would be 9. Okay, so that's how we would do it by hand, but we would certainly go through and do the binom. And let's keep it easy. I think most of you guys have kind of gone on to this one, binom.range, and let's use that as we go. Okay. So construct a probability distribution for this random variable. So X, our probability of that particular X our x goes between 0 to 11. Once I train it, I can do highlight everything and go to 11. Or I could just type all of these in. Hopefully it's not going to be very long. And then the probability is equal to the binom.dist. I don't use the range. This is why I use this one most of the time, because the number of successes, I'm just going to click on that. See where that's A2? That says this is the one that I'm going to use. My trials is out of 11. That's a constant. My probability of success is the 0.419. That's what I'm picking here, comma, and then it switches over here. Do I want the cumulative or not? No, I want the exact value because I'm building this probability distribution. The probabilities for that's what this is asking for. Construct a probability distribution for the random variable. Okay, so now I highlight it, do the fill handle, pull this down, and that's the probability distribution, right? You remember doing this? So if I go insert, recommended charts, and do the bar chart. Don't do the histogram, even though the Excel does not do it very well. It is painful to go through that thing. I fight it all the time. That's what you would kind of look like. That would be the probability distribution. We would shrink the range and stuff, or the distance between these two to make it nice. Format my data series. And here's my gap width. And then if I come here and go to 0, then there's no overlap. Okay? But that's the probability distribution. So then it says, determine the mean and standard deviation. Remember, let me pull this up. Let's back up, do a quick review. Discrete probability distributions. Discrete probability distributions. Discrete is only certain values. Okay, I can't have numbers between numbers and decimal places, and it's okay if I had 0.1, 0.4, 0.6. If this was the only values that I could get, then yeah, it's discrete. I could go between here to here, those measurements. But I can't say this and then go, okay, well, there's also 0.2 in there, and then 0.3. That would be continuous. Okay, so it's got to be a set number. Now, the general version of a discrete probability, the x's could be any value. So this could be -10, 0, 5, 20. Okay, and as long as we have something like, let me go 0.10, 0.5, let me go 0.3, 0.3, I'm doing this on purpose, 60, 70, so this would be 60, 70, 80, 90, and then maybe a 25, and then do it, let me, sorry, 0.10. Let me make sure this is working out, okay? It can only take on these values and particular probabilities. So this is 0.30, so 10, 40, 70, 80, 90, 100. This thing needs to add up to be 1. The sum of the probabilities equals 1. And 0 less than p less than 1. All of these have to be between 0 and 1. Warning, if you ever say, oh, the probability of something like this is 22.7, that is not the probability. There's no way that you can have a probability of 22.7. Okay? So, the reason I brought this up, if you just got a general probability distribution, the mean expected value, which is the same thing as the mean of this distribution, is the sum of x times p of x. That looks like -10 times 0.10 plus 0 times 0.30 plus 5 times 0.30, and I continue it out. Okay, So I get this number that comes out to be some mean, and then the standard deviation formula, that's the mean formula, and then I have the standard deviation, the square root of sum x minus that mean that I just calculated, squared for each one of these, times its probability. So this would look like for the first couple of them, got a big square root of everything. And for the first one, it would look like minus 10. Let's say this was 7. It would be that squared times 0.10, that probability for this, plus 0 minus the 7 squared times the 0.30. And I would continue all of these, add them up, and then take the square root. That's the standard deviation for those. Okay? For a binomial, I get a sweet deal. You're like, yes, this thing is binomial. The mean is just n times p. This is the expected value. Out of 11 people, with a percentage of the 0. Let me bring this back into the scope. 0.419 is 4.609. Okay, that would be the mean. That's sweet. That is much better than the sum of the xp of x. And the standard deviation is just n p 1 minus p. How sweet is that? 11 times 0.419. You can even take this and move this to these first two. Okay, times 0.419. That's going to be 4.609, but then you have to multiply it times 1 minus 0.419. Get these numbers, 4.609 times that, and then take the square root. And if I do that real quick, that would be, that I get is 1.636. Okay, so you're going to have to do that inside, you can do that inside Excel. Equals 11 times 0.419. 0.419, the 4.609, and then I would do equals, to do that square root, SQRT. So write that down as well. That should be on your formula sheet. And then the 11 times the 0.419, you could also put 4.609 at that point, times parentheses 1 minus the 0.419. Close parentheses for that one, and then one more to close up for the function, and that gives you the 1.636. Okay, again. So assume that the distance that a fly ball hit to the outfield travels is normally distributed with a mean of 250 feet and a standard deviation of 50 feet. What is the probability that an individual random fly balls what is the probability individual round travels less than 177? Okay. So this is asking, put it right here, I've got a mean 250, standard deviation 50 feet, normally distributed. I need that somewhere in order to do, I want to do the probability that an individual pick out whatever this thing is, and it would be less than 177. Out of all of the numbers, what are the ones, the proportion that's less than 177, or a random variable, a random pick of all of the, give me the distances, put them in a bag, pull out what would be the less than 177. And this normal distribution with this and this gets us to it, okay? To the left, here's the number, the mean, standard deviation, and then we always do 1. What is the probability that an individual random fly ball will travel more than 215 feet? Let me see if I can get this thing down a little bit like this, get us a little bit more use while maintaining that. Different question, what's the probability that that would land greater than 215? What's the proportion that more than 215? This is to the right. So if I drew that picture, 250, 215 would be to the left of that, whatever that is, but I'm just saying here I want that probability or that area greater than that. The only thing norm.dis does is to the left. Okay, so this is 1 minus, this is what I've got to find. And then use everything as 1. I'm going to subtract this a little bit to the left, and that's going to give me to the right. Okay, and so I would just go equals 1 minus norm.dis 215, 250, 51. And it would look like this in Excel if I pull up my Excel. Equals 1 minus norm.dis. So it's going to come up here. Here's your this. I did the not.s. Be careful with that. I want the norm.dist. Come on. The x value, that's the 215, my 250, my 50, and always do the accumulate, and that would be 0.758036. This picture, here's something that you kind of get used to in doing it, looking. Here's 250. That's the mean. Right, we go back up here. The mean is 250. Halfway is 250. Greater than 250 is 50%. 50% on the other side of the mean, 50% less. This is on the left, and I want that area, that big area, that's got to be more than 0.50. If I did this and come up with a number less than this, draw your picture, and then you would know, oh, there's a problem if you really sit there and think about it. Okay. Something would be amiss. What is the probability that the random individual random fly ball will travel between 270 and 370? You start out, you would say, okay, between the two, sandwiched between the two, this is what it would look like. I've got, that's what this is between these two numbers, the 370 and 270. Okay, the big area to the left minus this gives me the stuff in here. So this looks like I'm going to take it an x less than 370. That's this piece, and then subtract off the probability that X is less than 270. I know this is saying more, but what you're doing is subtracting off the less than the 270. Okay, and that's two versions, norm.dist, 370, 250. Finish that out. 250, 51 minus the norm.dist. And then that would be the 270. Mean standard deviation 1. Finish that out. Okay, here I've got one particular game sees 20 fly balls. How many would you expect to travel more than 310? You remember the probability. If I've got the probability, now this, your first glance you're saying, is this a binomial distribution? Okay, the binomial distribution tells you all of the probability of, from the 0 to 20, but you have to have that percentage to even get the binomial thing. So you've got to get a percentage out of this piece. What would be the percentage or proportion that would go greater than 310? So you have to first come up with, well, what's the proportion? Everything is 100%, 100%. And then you're looking for the greater than 310, that proportion. Here's 310. So you want that proportion, that percentage, that probability, they all come out to be the same thing. Okay, so that's what we're looking for. And this has got to be 1 minus norm.dist. 310, the mean standard deviation. Equals 1 minus, let me open this thing up for you just a little bit. Close that, do this. Okay, so let me get here. And then this would look like equals 1 minus the norm.dist the x is the 310, the mean, what is the 250, 50, and we always accumulate. So that would be the area or the proportion that's greater than 310. So this number is 0.11507 or 11.507% greater of the balls are greater than 310. It's asking you out of how many, if it did 20, out of 20, how many would you expect? The n times the p. Now we know the p, the expected would be n times p, okay? So out of the 20, the percentage is, we got to use the decimal, 0.11507. So we would expect, this number is 2.30 on average. We would expect 2. We're going to be generous. We're going to go down. Could be 3, but at 2, I would expect 2. I don't want to do the average, like the mean. I want to say this many balls. So that would be, we're not going to chop up a ball. Okay. What is the cutoff distance for the top 10% of fly balls? What is the top 10%? I want to know where this is. I'm asking if I did our normal distribution curve, here's 250. 50% would be greater than 250, right? But I want to do the top 10%. That area in here is 0.10. That would be the top 10%. I need this break value, okay? This is the normal inverse. Norm dot inverse. Area to the left is the 0.90. 1 minus 0.90. This isn't the over 2 because I'm not doing 2 tails the middle. This is to the left, so 1 minus 0.90, 1 minus 0.10, which is 90% here, 0.90 probability, and then we're going to do the 250, 50, okay? So this number is 0.90 to the left. So the probability, that's the 0.90, 250, comma 50. And that number, this breakpoint is 314.0776 feet. So 90% of the balls are less than this number, 10% are at that or above, okay? That's kind of a break number. So we're gonna leave, that's just the number, the break point. Okay, and then it says, what range of distances for fly balls could be considered usual? Justify your reasoning, okay? The usual that you're going to look for, the probability is 0.05. That's your comparison, okay? So if you have some probability less than 0.05, if you're getting the probability of something, then you're getting more extreme. So if I wanted to do this and do it in the middle, I'm doing the area in here, doing the X value, or 1 minus 0.05. So that area, everything is the 0.95. So I'm going to run these two numbers, and that would be the range. Anything outside less than this would be unusual. Greater than that number would be unusual. Okay? So I'll do that real quick, just so we'll have some sense of working. I just wish that would have stayed the same magnification. So this would be equal to norm dot inverse. The 0.05 is what I would be looking for. And then the 250, 50. So anything less than 167 feet and anything more, I want to grab this thing down. This will be, everything is going to be the very same, and then I'm just going to change this number to be 0.95. Anything greater than 332 feet, the probability would be less. Okay, so these two numbers are what they're asking for, 167 and then 332, ... But anything over 332 feet, the probability of it being more than this would be less than 0.05. The probability of any ball being less than 169 would be less than 0.05, and that's the comparison. Those are the extreme values. Okay, so let's go over this one real quick. A student conducts a study for a sociology class where he researches the net winnings for several lottery players. He writes a report. Here's his thing. Okay, is this a valid probability distribution? Remember a while ago I had two different criteria. So I'm going to go down -5, 0. These are my X's, 15, 95, 195, 995. So if I raise this up now, I should have -5, 0, 15, 95, 195, 995. These are my X values, and then my probabilities. I'm going to do the very same thing. So this is 0.875. I'm going to check right in here to make sure everything else, 0.104, 0.015, 0.005, 0.003, 0.001. Looks like everything is between 0 and 1. They're positive numbers. Between 0 and 1, that's good. And now I need to make sure that they sum to 1. So I'm just going to select and enter. And I get 1.003. Could have been a mistake, but in this case, they're going to come back. So this is not a good probability distribution. It's not, okay, we just rounded some numbers wrong. We need to go get them a little finer. These were wrong because they added up to something different. And then it says, the student realizes that his probability for the net $15 is incorrect. What must be this probability in order for this distribution to be a valid probability distribution? Okay, so the one for the $15, this is wrong. Okay, that's wrong. It needs to be 1. Everything needs to sum to 1. And then I need to subtract off all of these, minus this one, minus 0.104, minus 0.005, minus 0.003, minus 0.001. That needs to be 0.012 to get everything to 1. Then this is a valid probability distribution. Okay. Calculate the expected value of the winnings. So if he played this thing over and over and over again, what would what would all his average be? What would be his average winnings? And per game, I guess is what we would do. And this is X. What I'm going to do is just multiply the X times P of X. I would do this in Excel. You would have to do this thing up and add it if you're doing calculator wise. Do it like this. This times its probability, and then drag down, and then sum. So he would go in the hole $2.14 on average. He may win $995. Okay, here he takes $5 to play for a ticket. Here he won $5, so his net winnings is 0. $15 after he paid back 95. Sometimes he may do this, sometimes, but over the long run, his expected to go in to be an average of $2.14 in the hole. Okay. And then it says, calculate the standard deviation of that distribution. So remember the mean or the expected value of X, different ways that they're going to ask the very same thing. This was sum up all the X times P of X's. And then my standard deviation was, once you've done this, you've got to get this first. add up the x minus your mean squared times p of x. So in order to do this, this is how I would do it. I do the mean first, and now I do for each one of these things. So let me just, this would be x minus mu squared times p of x. This is what I'm doing. This is the formula. Okay, and then I'm going to sum them up. Then I'm going to sum them up, and then I'm going to do the square root part of it. Okay, so this is equal to, I need to put a couple of parentheses. I'll show you. I've done this recently, and I know I need to put a parentheses around here and a here. So this is, okay, no, I don't want to do that. I just want to show you this. I need to put this in front of here and here. Okay. Make sure it's not trying to do 2 times p of x in here. Okay, so equals, a couple of parentheses, the x value minus the mean, which we've calculated here. So I'm going to put minus a negative 2.14, close parentheses. That one's for the negative there. So this would be actually plus 2.14. That squares it, multiplies it times itself, and then times each individual probability, and that one is from there. Okay. So that's what that individual piece of it does. And now, since everything, I can do this, it calculates each one. And then I need to sum this up. And then I need to do that square root. And that gives you that. Okay, so that's how you do in Excel the mean and the standard deviation. Okay, so let me again for this review, and then that's not what I wanted. Get rid of you. Okay. Here's z-scores. I think we worked on these things before. Z-scores back and forth. I wanted to do some central limit theorem problems, so that's kind of, let's finish up on these. Make sure we talk about the central limit theorem. Central limit theorem says I started with some population, okay? Population data. Here's a sample. I took a sample, and this is a particular size. So now I've got to say like n is equal to 40. Okay, so I've got a sample from this. Okay, if I know what the mean is and the standard deviation, like before, what would be the probability of x being less than, let's say, 200? Okay, that's the problems that we worked over. Okay. But now it's saying a couple of versions. I did this and I got an X bar. Okay. What would be, this is no longer an individual. It says, what is the probability that the X bar is less than, let's say, 260? The mean of this sample, and it all depends on n. So that gets us to this. When I'm talking about the average of the sample, then this is the central limit theorem. And it has a couple of criteria. Either the population you know is normally distributed, or if n is greater than or equal to 30, then the mean that I'm going to use, and I can do this, the mean of the x bars is the mean that comes from here, right? And then the standard deviation of the x bars is the population standard deviation divided by the square root of n, okay? So let's take a look at this and let's see how this works here. You randomly select, in 2005, let me go back over. In 2005, student scores on the math section of the SAT followed a normal distribution with a mean 540 and a standard deviation of 115. Normal distribution, okay? Now you randomly select 26 students who took the SAT that year. Can we use the central limit theorem to determine the probability associated with the group's average math score? So number one, if this wasn't normally distributed, I couldn't ask the probability of a particular one. But if it doesn't really matter if this is normally distributed or not when I'm doing the central limit theorem, as long as I had bigger than 30, I don't. But as long as that population is normal distributed, I can. So the answer to this is yes, because the population is normally distributed. You randomly select 35 students who took the SAT that year, determine the mean and standard deviation of the sampling distribution. Okay, so this is what this is called. This whole thing, or a particular size, whatever this size is, I said 40 up there, but this is the sampling distribution. I took a bunch of samples of 40, averaged them out. The mean of the means of those samples was the mean of the population. This turns out to be this. If I had all the data, this would work out to be what that is, okay? So now, let's go to the numbers. It says, normally distributed, that's good to know. The mean is 540, and the standard deviation is 115, okay? Then we pull down, and it says I took a sample, so here's a sample, of 35 students. I'm going to do the X bar, and that would be, I need a mean and a standard deviation to ask questions like, well, what would be the probability of that sample mean being less than a number? I need the mean of the sample means. Well, I get that from the population. That's 540. The standard deviation that I'm going to use is going to be the sigma over the square root of n, which is just the 115 divided by, my n was my 35, square root of 35, okay? So now, once I get to this, I can say, do the normal distribution, whatever this thing is, so that's what I'm going to use. Let me see what the question is. What is the probability that a group of 35 who took the SAT will have an average math score between 550 and 575? So this is asking, what is the probability between 550, 575, sandwiched in, and not X, an individual, but the mean of the sample. The mean of the sample. And then I do the norm.dist. So this one is norm.dist. The 575 with the mean, the standard deviation, SQRT is what you would do here, 35, comma, accumulate, minus norm.dist 550, the smaller one, 540, 115 over SQRT, 35, comma 1. So that looks like in Excel equals, so norm.dist, the 575, the mean is 540, and now for doing this, I do 115 divided by SQRT. The size was 35, and then I finish it up with the true always accumulate. That would be the area to the left of 575. This would be the 550. I want to change this number to the 550. That would be the number to the left of the 550. And then the area between the two is just the big area minus the little area. And that's what this all would be. I could do this all on one line. I could do this minus. Okay. So let's do one more. Let's make sure we can do a CLT. I think this is the CLT. 69% of adults surveyed will use some long-term care. Among those who do not use, 20%. What is the probability that a randomly selected U.S. adult over age will not need long care? Okay, so this is just kind of, anytime we're doing with percentages, p-hats, we're doing two categories, and it's just asking you, it's giving you this data, 69% will use some variety of long-term care, then what is the probability will not need long-term care? So that's just the 100%, or the probability would be 0.69 that they did, and then that would be what, 0.31. That's what A is asking. It's just letting you know the category that will need it, and then the other category will not need it, okay? What is the probability that a randomly selected U.S. adult over age 65 will use long-term care for more than 5 years? Okay. So here, the probability of that will require it for more than 5 years. So here is the probability of A times the probability of B given A. That's that situation, okay? So this is saying, B is saying, what is the probability that they will be, a randomly selected will need it? Well, it's the probability that they will need long-term, and then the probability that it's greater than 20 years or greater than 5, given that, that they need the long-term care. So this is the 20. So this is just the 0.69, 69% of the adults times the 20% that's going to be longer than there. So this is the probability of A, and they need long-term care. Over 5 years, more than 5 years. That's what that looks like. So this probability is just 0.138. Okay. So the rest of them, I think you guys know these. You just continue practice. Go over study material. You have to take your test before 8 in the morning. So get over on that. Any questions